Okay, you see. Okay, hold on. First of all, what do you mean by you are in motion? Well, your claim is, okay, so if I'm in motion, length should be contracted. If I'm not in motion, length shouldn't be contracted. Kind of like that, right? What do you mean by you are being in motion? No, I mean, what do you mean you are in motion? I'm not asking your speed. Relative to another reference frame, you are in motion. So you are there. Let's say there is one reference frame fixed at you. There is another reference frame fixed on me. You are in motion relative to my reference frame. I'm in motion relative to your reference frame. Okay. So then you are talking about length. Length with respect to which reference frame of which object. So first of all, when we are talking about the length of an object, well, we usually mean its length in its rest frame. That is one frame. That is the length of the object. If the object is moving relative to my reference frame, I will observe a length that is shorter. That is what we mean by length contraction. Now let's go back to this example of the muon. In my reference frame, or in the reference frame of the Earth, muon is moving at speeds close to the speed of light. So there's time dilation, and due to that time dilation in this reference frame, it will seem as if it is living a very long time, and during this time, the muon can reach the surface of the Earth. That is what I will observe. Now let's go to there's a thickness of the atmosphere also. So it crosses all that thickness. Now in the reference frame of the muon, well, the atmosphere is moving. So if you just imagine a meter stick that starts from the surface of the Earth and extends up to the top of the atmosphere, in the reference frame of the muon, in which the muon is at rest, that stick is moving. Since that stick is moving, it will be Lorentz contracted. So the atmosphere will be much thinner, much narrower. So in his reference frame, in the muon's reference frame, the muon lives a very short amount of time, and in that amount of time, it covers a very short distance, but that short distance is still larger than the thickness of the thickness of the atmosphere, which is Lorentz contracted in that reference frame. In that reference frame, the atmosphere is very narrow. Well, I mean, it's an unstable particle. It doesn't just naturally occur by itself, but we do create, I mean, we have these cosmic rays that come from the space. They are very high energetic. When they collide with the particles in the atmosphere, they create some of their energy is converted into mass, and they create mainly pions. And these pions are still unstable particles. They don't naturally occur most of the time. And they decay. And when they decay, they dominantly decay into muons. So the muons most of them are produced by the decay of the pions, which are created by these cosmic rays.
Hocam bir tane parçacıktan bahsediliyordu. Böyle ışıktan hızlı hareket ettiği için zamanda geriye doğru gidiyormuş.
No.
Evrene geçiyor.
No.
Öyle bir şey yok mu?
No.
Takyon diye bir şey vardı mesela.
That was a hypothetical particle for which m squared is larger than 0. But we now know that that just means that we are not in the real vacuum. For example, Higgs is a tachyon. It doesn't move faster than the speed of light. It is very slow. It is at rest. It's so heavy that it doesn't even move. So that's a long story which I would rather avoid. At least not during the lecture. And the backwards moving particles are called antiparticles. So it's basically a mathematical similarity. Mathematically, an antiparticle moving forward in time is the same as a particle moving backward in time. But that's just a mathematical equality. You see, that is just a mathematical similarity. Now, let me ask you another question. You see, we have seen that in the reference frame of the muon, the atmosphere is very narrow. But that doesn't mean that there are less particles in that reference frame. We have the same number of particles in that reference frame. Furthermore, if you insist on defining an effective mass, in that reference frame, the mass of that effective mass of the atmosphere, although it is now narrower, it is much larger because it's moving with some velocity v. So there is more mass in a smaller volume. Well, that means the density has increased. Well, that also means that the density is a frame-dependent quantity.
Mass aynı kalsa gene volümü azaltıyor.
Sure, hence the density increases.
O zaman gene efektif massa ihtiyacımız yok.
Sure, but that's another factor. But even without the effective mass, if you just stick with the ordinary mass, the density increases.
Miyonlar şimdi atmosferden gittikten sonra sonuç olarak başka gazlar var. Aşağıdakilarda şarkı söylediler. Bunların absorbanmalarına neden olur mu?
Sure, I mean not all of them reaches here, but we more or less know how much of it will be absorbed.
Belli olmasını.
Sure.
Peki density artarsa bu olasılık değişir mi? Hani
Well, let me connect this increase in the density to something else, and then let's come back to your problem. Well, the increase of density is a problem for space travel. Not now, but probably in the future. Let's suppose that we develop our technology so that at least some devices can move close to the speeds of light. And as far as we know, we have more or less that technology. I mean, we can send objects at speeds close to the speed of light. But then the problem is the universe is filled with gas. It is very dilute. You don't feel it. I mean, it doesn't really affect anything. So the density is very small. But if you are approaching speeds of light relative to the rest frame of the matter in the universe, but that means the density will increase. So that object will feel a huge density of hydrogen. Well, it will probably burn because of heat. There will be friction. Once the density is large enough, the effects of friction will be non-negligible, and hence in his reference frame at least there will be a huge friction and it will probably burn. So forget about reaching the speed, passing the speed of light. We cannot even reach it actually. Not because of the technology, etc., but mainly because of this dilute gas in the universe. Now let's come back to your example. What do you mean by probability? Which probability?
yani parçacığın atmosferde giderken hani başka bir gaz karşılaşma olasılığı.
Sure. I mean, you see, the sensible quantities would be, for example, the probability that it will be absorbed per unit time, for example. Well, time changes from reference frame to reference frame, so this concept changes. Another thing that you can define is the probability that it won't be able to reach the surface. Well, that probability will be more or less the constant. Because if in one if you count the muons, the number of muons do not change from reference frame to reference frame. if 4 out of 5 muons can reach the surface of the Earth in the reference frame on which the Earth is at rest, well, it will be the same in the other reference frame. But of course, if you talk about the probability that it will be observed as it covers a given distance, again, this time also distance changes from frame to reference frame, so probability per distance, probability per time, these will change. But the probability of reaching the surface of the Earth will not change. Basically because if you talk about, for example, the probability of reaching the surface of the Earth will be kind of related with the probability per distance summed over all the distance. So both the probability per distance changes, sum over the distance changes because the length of the atmosphere changes. They will cancel each other.
Hocam bu derste fotonlara girecek mi?
No. Yes and no. Because we already did the photons. What we call a photon is just an electromagnetic wave. Why do we call it a particle? That we will not discuss. No. You might be doing it partially in quantum mechanics. Not in quantum physics, but quantum mechanics. When you take quantum mechanics, you will probably see it. So the problem is first you have to define what you mean a particle. And then you can study what is a photon. Let's look at another example. Let's look at a dipole. Well, before looking at the dipole, let's look at two concentric cylinders. We send some current through the inner cylinder and take back current from the outer cylinder. Let's also assume that we have some surface charge density on the inner cylinder. Let's not say surface charge density, but linear charge density in the inner cylinder, and minus the same linear charge density on the outer cylinder. Well, this is both a problem in electrostatics and magnetostatics. Nothing changes in time. What is the electric field in the region between the cylinders? If we just imagine a cylindrical Gaussian surface of height, let's say h, the total charge enclosed will be lambda times h. Let's divide by epsilon 0. Divided by the side area will be just 2 pi rho times h. It will be in the rho hat direction. I'm not going through the derivation of application of the Gauss's law. So h's will just cancel. E will be just 1 over 2 pi epsilon 0, lambda over rho in the rho hat direction. Well, you see, if you look at it from the side, here I have plus lambda, here I have minus lambda. So the electric field is pointing outward. So it's in the rho hat direction, assuming rho is positive. If rho is negative, of course, it's in the minus rho hat direction, but it's already here. Well, we can do the same thing for the magnetic field. B will be the total mu0 times Well, the enclosed current, if you just imagine such a loop, the enclosed current will be just I divided by the circumference of this Amperian loop, 2 pi rho. Let's say this is my z direction, so it's mu 0 I over 2 pi rho in the phi hat direction. Let's calculate the pointing vector. This is 1 over mu 0 E cross B. This is equal to 1 over mu 0. E is 1 over 2 pi epsilon 0 lambda over rho. B is mu 0 I over 2 pi rho. And the direction is rho hat cross phi hat. Well, let's say this is the z direction. In this figure, if you, let's say this is the z direction towards the right in the above figure. If this is the z direction, let's look at over here. Phi hat is this vector at that point. This is rho hat. So rho hat cross phi hat is in the z hat direction. Well, in fact, even if you look at some other point, let's say over here, this will be our rho hat. Now this is phi hat. This will be our rho hat. Rho hat cross phi hat, wherever you are, it's always in the z hat direction. So S is equal to, let's cancel these mu zeros, lambda I over 2 pi epsilon 0 rho squared 4 pi squared epsilon squared in the z direction. P squared. Well, the momentum density is just S over C. This is equal to lambda I over 4 pi squared epsilon 0 rho squared in the z direction. Let's say this has a total length L. Well, we are, of course, neglecting the fringing effects. I will be assuming that L is long enough so that the regions where you observe this fringing effects is very small compared to the total size. So I can talk about the total momentum of this system. Now, the total momentum in the electromagnetic wave is just the integral of the momentum density over the volume, which will be, well, the volume integral contains the dz, and the area integral, well, area integral contains the phi from 0 to 2 pi, dz, let's say, from 0 to L, and then we have rho d rho from A to B. Let's say the inner cylinder has a radius A, the outer cylinder has a radius B. The momentum density is lambda I over 4 pi squared epsilon 0 rho squared in the z hat direction. Well, this rho will cancel one of these rho. So if you just evaluate the integral, this phi integral just gives me a 2 pi. It cancels a factor of 2 pi over there. The z will just bring a factor L. So this will be just lambda I L over 2 pi epsilon 0 logarithm of B over A in the z hat direction.
Işık hızı ne yoktu? C.
Yes, you are right here. I forgot a factor. C, C, C.
Hocam fırıncık efekti ignore etmeseydik.
Well, you will get a much complicated expression of the electric field and magnetic field close to the edges, and hence the result will be much more complicated.
Additional term.
Yeah, I mean, you can write them as corrections, or just you will end up having some integrals that you won't be able to evaluate. Now, nothing is moving, but we have a linear momentum. So if you just imagine, for example, oh, okay, nothing is moving and there's linear momentum.
Ama yükler hareket ediyor.
We have charges moving in one direction and charges moving in the other direction. But you're right. Well, this is the linear momentum in the fields, not in the charges. And basically that is what we are neglecting. We should also add to this the total, to calculate the total linear momentum, we should add to this the linear momentum due to the moving charges. That is what's called the hidden momentum. Now let's study this hidden momentum in a simpler system. In this system it will be a bit more complicated, but let's just look at a simpler system. Let's look at a dipole, a magnetic dipole. Let me exaggerate it slightly. So this is my wire. There's a current running around this. Let me just assume that there are positive charges moving around. Etc. Now, what is the direction of the magnetic dipole moment? Into the screen. This is just this is the direction of the current, since it's positive charges. So it's into the screen. Now let us assume that we have an additional electric field also. We add an external additional electric field to our system. Now, due to this magnetic dipole moment, there is a magnetic field. We add this external electric field. So E is non-zero, B is non-zero. E and B, they are not pointing in the same direction, because B would be mainly just, it will be into the screen in between in between the magnetic dipole, and out of the screen at the outer regions of the dipole, this magnetic dipole. So B will be perpendicular to E. So E cross B will not be zero. And there will be some linear momentum stored in the electromagnetic field. But as your friend has pointed out, there should be some linear momentum also due to the moving charges. I will assume that the system is in general neutral. So at the top region, let's say there are n plus positive charges. At the bottom region, there are n minus positive charges. Well, plus and minus, they don't refer to the charges, but it's in the higher, it's in the lower region. Plus is the higher, minus is the lower region. Let's say this length is L. Now, if you assume that the system is neutral, so n plus should be equal to n minus. That is one thing we have. Sorry. Let's forget about the neutrality, because neutrality, it will be inconsistent What I want is that the current is constant. That's what I want. Neutrality will be a different problem because there's an external electric field applied to the system. The system will not be neutral everywhere. There will be some local charges. There will be more positive charges at the top, more negative charges on the bottom. So it won't be neutral. But what will be still satisfied is that the current will be the same. So these charges at the top, they are, let's say, moving with speed u plus. Those charges at the bottom are moving with speeds u minus. Now what I want is n plus u plus should be equal to n minus u minus.
Çünkü bu n number of particles.
Yes. N is the number of particles at the top region, and plus and minus is the number of particles on the bottom region. Of course, if you want, you can also talk about the number of particles on the left-hand side, on the right-hand side. But you see, the problem is u plus and u minus will be different because of the electric field. The positive particles are accelerating, so they are moving faster over here. But on the right-hand side, they are decelerating as they are moving toward the bottom, so they are moving slower on the bottom side. So u minus is smaller than u plus, but for this equality to hold, n minus is larger than n plus. Now that kind of makes sense. You see, if you just imagine a traffic here, the traffic is moving slowly, so there are more cars that accumulate over here than the n plus is at the top region where the particles are moving very fast. If you forget about special relativity, on the left and on the side, if you look at some charge over here, it will have the same speed as some charge over here. One will be moving up, the other one will be moving down. So the densities on the left and on the right, they will be equal to each other. Now, if you calculate the total momentum of the system, you see the total momentum of the system will be, well, on the left and on the right, they will have the same magnitude. But it's just one is pointing upward, the other one is pointing downward, so the sum will be 0. So if there is any total momentum in the system, it will be basically due to the charges on the top and the charges on the bottom. But on one hand, the charges on the top, they are moving faster. So each one of them have a larger linear momentum than each charge on the bottom. But nevertheless, there are more of them on the bottom. So ignoring relativity, the total momentum of the charges, let's say this is my x direction if you like, will be n plus. I have n plus positive charges, each one having a mass m. They are moving with a velocity u in the x direction. I have n minus particles having a mass m, moving with a velocity minus u minus in the x direction. And this will be equal to n plus u plus minus n minus u minus m times in the x hat direction. So ignoring relativity, this is just 0. So even if we have even if the charges are moving, well, some of them are moving in this direction, some of them are moving in the other direction. So they again cancel each other. Again, I repeat, if we ignore relativity. Now, where will the relativity come into the game? So, what should I modify to take into account the effects of relativity? You see, length contraction is only valid if I change my reference frame. I'm just sticking with a single reference frame. I'm not considering any change of reference frame yet. I'm just looking at my problem. I'm looking at electrostatic case when the static configuration is reached, because, well, I'm sending some steady current. If, since I'm looking at a static case, the current should be the same everywhere along the wire, otherwise there will be some accumulation of charge somewhere. I use that condition over here. The requirement that the current should be the same everywhere just gives me this relation. And if I use that relation, and here I ignore the relativity, this is the step where I'm basically ignoring the relativity. If you ignore relativity, momentum is just the mass times the velocity. But then we have the relativistic corrections. So with the relativistic effects, the linear momentum of the charges, you see, will be n plus m u plus in the x hat, but then I have a gamma factor. This 1 over 1 minus v u plus squared over c squared. Minus n minus m u minus x, but then I have a factor of gamma minus. Now I can use the fact that n minus u minus is equal to n plus u plus, and I would end up having this is equal to gamma plus minus gamma minus n plus m u plus in the x hat direction. Is it in the plus x direction or the minus x direction? This linear momentum.
Plus x direction.
Why? You see, the question is basically, is this number positive or negative?
O aslında sıfır değil mi? Eğer bu u plus u minus birbirine eşitse.
Are they equal? There's an electric field and hence they cannot be equal. U plus is larger than U minus. Now gamma plus minus is defined as 1 over square root of 1 minus U plus or minus squared over C squared. Well, U plus is larger. So for gamma plus, this factor is smaller. Gamma plus is larger than gamma minus. So the linear momentum of the charges are in the positive direction. What is the direction of the linear momentum in the electromagnetic field? Well, of course, it will have a complicated shape, complicated expression, etc. But nevertheless, we can still say something about the direction. Let's look at the direction of the magnetic field. What is the direction of the magnetic field inside my dipole? Into the screen. Outside. Out of. Now, what is the direction of the pointing vector? Out of the dipole, in this point, for example, it's in the x direction. At this point, also in the x direction. And here we have, well, if you calculate the total linear momentum of an ideal dipole, eventually we will just take this to 0 anyway. So there won't be any contribution over here. So the momentum, linear momentum of this system will be in the plus x direction. Now let me also write one more thing. Now let me leave it over here. Okay, so we have the charges have gained some linear momentum in the plus x direction that we call the hidden electric dipole, and the minus charges and the electromagnetic field also acquires a linear momentum. It seems to be in the same direction. Now let's try to calculate this gamma plus minus gamma minus. Can we relate it to the electric field? You see, the energy of, let's just look at one particle. The energy of that particle will be m times gamma, mc squared times gamma. It starts with energy E minus, which is mc squared gamma minus, and it ends up, when it reaches the top, with an energy E plus, which is mc squared gamma plus. So the change in the energy of my particle is mc squared gamma plus minus gamma minus, or gamma plus minus gamma minus is the change in the energy of my particle divided by mc squared. But you see, the change in the energy of the particle is nothing but the work done by my electric field. Let's say this is my dipole. Let's call this length W. So delta, the force acting on my charged particles, is fixed. It is just Q times E, the external electric field I applied. It acts on my particle for a distance omega divided by mc squared. Now the momentum of the charged particles hence turns out to be q e omega over mc squared times large M times n plus u plus. In the x direction, m's will just cancel, and I should have a factor of, no, okay, yes. N plus q, well, n plus is nothing but the charge density at the top part times the length of that top part times u plus x hat over c squared. Well, let's see, I have the charge density multiplied by the velocity. Well, that is just, well, this is the linear charge density, so this product is nothing but the current running in my loop. Well, okay, that rho plus is the number density multiplied by charge gives me the charge density multiplied by the speed of the charges, that gives me the total current. So this is omega Li over c squared x hat. Well, omega L is nothing but the area of my dipole. I is the current running in my dipole, so this is nothing but the magnetic dipole moment of my system. Well, let's look at the directions. The magnetic dipole moment is into the screen. So if we just consider mu cross E, that is in the x hat direction. Well, mu and E in this example, they are perpendicular to each other. So their magnitude, the magnitude of this vector is just mu times E. It's the magnitude of this vector over here. If you look at the directions, mu cross E is in the x hat direction. So E mu x hat is a vector that has the same magnitude and direction as mu cross E. So they have to be equal. So this is the expression of the so-called hidden linear momentum due to the motion of the charges, as your friend points out. But this is again purely a relativistic effect, which is also apparent from this c squared over here. This is due to the increase of the effective mass, if you like, of the particles that are moving faster. Okay, any last questions?
Hocam burada bulduğunuz pi elektrik alanındaki lineer momentum değil mi?
Yes. In the previous case where we had these cylinders, we have these charges. It is due to the motion of the charges.
Hocam şimdi bu parçacıkların hareketinden dolayıysa
No, I'm not saying that that's, I mean, you see, the previous expression okay, in this case we had calculated the linear momentum in the electromagnetic field. What I'm claiming is that's not the total momentum. Although nothing seems to be moving, the charges will be, well, in this case it's kind of, you see, what is the hidden momentum in that example? Is there a hidden momentum there? The hidden momentum there is zero. You see, because the charges are moving with the same speed, both in the inner cylinder and the outer cylinder. So there is no hidden momentum over there. In the other case, in the magnetic dipole case, there is a hidden momentum. Well, in this case, there are two kinds of linear momentum. One, the linear momentum stored in the electromagnetic field, because we have both the electric and magnetic field in this example, just like in the previous case. But there is also this hidden momentum in this case. Well, let's see. If E is zero, there is no hidden momentum. Well, in the previous case, I don't really need that additional electric field because the system already has an electric field of its own. I don't need an external one. Well, if you apply an external electric field, things kind of start to get kind of complicated because the electric field, there's an electric field outside, and if you want to calculate the total linear momentum, eventually you reach distances which are large compared to the size of these cylinders, things get complicated. Now the thing is, either in the above one or in the below one, how do you relate this to momentum conservation? You see, the idea, nothing is changing in these systems. But let's say if you make some changes. Suppose you are changing the current, for example, in the above system. Let's say you are decreasing the current. Will there be an additional electric field? In which direction will this additional electric field will be?
azalmayı dikkat edecek.
Check it. Will it be? there will be an electric field which will cause the cylinders to start moving. Then now we might end up having some hidden momentum. If one cylinder starts, if both of them move in the same direction, for example, let's say, or if both cylinders start moving at different speeds, they will feel different electric fields in the above case. The inner cylinder and the outer cylinder will feel that there will be electric field will be different. Well, if the electric field is different, then they will start accelerating with different accelerations. If they are accelerating at different accelerations, this lambda will also contribute to the current, not just I. So the current inside and current outside will be different. If the current inside and current outside will be different, that would basically give me some kind of a hidden momentum. So the momentum of the electric field, as you are lowering I, let's say, you are switching off the battery. Now there's no external force, so momentum should be conserved. So the momentum in the electromagnetic field should somehow go somewhere. It will be the motion of the charges. Anyway, we will continue on Monday. Any questions?